Hello and welcome back to Risc-V emulation in a high-level language. Last episode, we finally got our assembler to emit full-blown ELF files, which was a big milestone and very exciting for myself personally. But the assembler that we have today doesn't actually take advantage of the power of our ELF builder class, which is creating these ELF files. In particular, there is no way in our assembler today to support more than one segment. So today's session is going to be refactoring the assembler and the linker so that they can emit multiple segments, not just two. And to motivate this, I will write a little sample test program that will have references to both data and code. And let's see if we can figure out a way to make our assembler and linker, assemble and link this into an executable program. So let's jump straight into this. And we have our project over here. Let's go to the test environment here and look at our text assembler. So what I'd like to do is extend the assembler so that I can do things like this. So we'll have a test program, and I won't be able to use run test because run test assumes that there's only one segment. So let me put a little comment here. And this program that I'm about to create will have more than one. So we'll steal this code, but then we'll change the way that it generates its output. So let's create a new method called run test2, and it will take some assembly language source, and then we'll put it in here. And it also needs, we won't be needing to compare it against some other sample sort because we are fairly confident that our text assembler and our internal assembler are working correctly. We have other unit tests to cover that. Instead, here what we want to do is take the output of the text assembler and use the ELF builder to generate a file that we then dump as hex bytes. So we'll say so now how do we generate the code today? Let me cheat and look that up real quick in the program, actually in the assembler. Yeah, that's it. This is it. So right after we assemble our file, we have a linker that does all of this stuff. And so I will do something similar. We need to define what base address is. We'll make that something like that. And then M is actually TASM. In fact, let's just do that by doing this. And then we need to add a reference to ELF builder. And then we are able to build our binary. And let's do that the way we do it over here. But instead of writing it to a file, we'll write it to a memory stream, and then we'll use that memory stream in our dumper. So we'll say that. And then we'll have a hex dumper. And the hex dumper will generate, let's see, what does it need? It needs a memory. So we need a memory. So we'll create a memory. Which will contain the whole contents of the memory stream. So we'll need to put that. And then we dump that memory. Let's call this the file contents. Make that a readable page, and then we dump it into a string writer. So we'll need a string writer, and then we tell the dumper, please dump your contents into the following text writer. And then finally, we extract a dump out of this string writer. And then we assert that sActual is equal to as expected. Right. Okay. And then we called it file contents. Good. And then we need to pass in an expected string. And now we're finally ready to use run test 2. So we will pass in the source and the expected. So what does this source look like? So here's my little assembly language program. I would want to, by default, if I haven't specified anything, I want to start writing data into the text segment, the executable code segment. So here I'll have an instruction like, oh, I don't know, how about jump and link register 0, 1, 0, which is the return instruction. It's pretty harmless. But then what I'd like to do is switch to the data segment. So what this is a directive. The dot and the prefix strongly hints that this is not an actual assembly language instruction, but a directive to the assembler telling it, please switch now to the data segment. Now the data segment will contain chunks of data, so maybe we should have here some writable data. Maybe we'll have my word, and then we'll say define word, and then 0. So this should, actually, let's make it something that we could recognize in the output. So we'll have that. And then maybe we can switch back to the text segment. And then we can do how about we call this instruction here? So we'll say returning. And then here we'll say jump and link returning. And let's make sure that we are using the right number of operands for jump and link. It's been a while since I looked at it, but it looks like we need to provide, let's see, where do we have it? We need to specify the register where we put the return address. So that would be the correct way to do that. And then we'll do another like that. So that is my little program. But then I also want to define what expected is. And expected is some big blob of binary bits that I don't know yet. So I'll just put a placeholder here for now to make the code compile. All right. So let's run the unit test. And of course it will fail because nothing is implemented yet. And then we go about refactoring our way to success. Oh, we are missing something here. Let's reuse this logger. That. Let's do this again. So this will fail, of course. And the first thing that it will cause a problem is these new directives. It doesn't know what data and text are. So if we look at the test results, we're not seeing the error messages, but we're not getting any data out of the assembler because it failed. It didn't succeed in disassembling our program. So what we need to do is implement .data and .text. And recognizing these directives is easy. We'll go to the text assembler and we'll add them. So we'll look for DW, this file, or not. I'll change it to .word. Here they are. Oh, it looks like I don't have a DW, so let's add one then. So we need a DW and a handler for assembling words. We also need a handler for .text and .data. So there's data and text. Good. So let's go to ASMDS and steal the code. So to define a word, what we'll do then is just call the inner assembler, but we expect, we have to parse the word that follows the DW directive. So we'll have to say var word is equal to asm expect immediate. That should give us an integer. Let's do that. And then once we have that, we also expect an end of line. So if we go back to our sample code here, there's our DW followed by something that is an immediate value. So that works. All right. So after we've expected the end of line, we can then tell the inner assembler, hey, create me a word, and here it is. That was shockingly easy. Okay. Well, how about these two new directives, though? We need to implement these two methods, and to do that, I will put them over here. So So what do we want to do? Well, first of all, the directive is a standalone directive. There's no operands or any other arguments for it, so we expect an end line right after the directive. So let's take care of the parsing of that line first. So this corresponds to the unit test where we see .data and .text with no operands coming after them. So we expect the end of the line after them. Fantastic. But then we want to tell the inner assembler, hey, I want to switch to a different section. And here's the name of the section. And here is the access mode of that section if it hasn't been created already. If it has been created already, then we just switch to it without any other thoughts. So I want this method to exist. I want to be able to tell the inner assembler, whatever you're assembling from now on should go into the data section and not into the text section. And then that's it. And similarly, for the text directive, the text directive looks like this. I'm asking the inner assembler, please switch to a section called .text. If it doesn't exist, please create it using the following access mode. Good. So now we need to switch section. So that's going to be a change. Let's go ahead and generate that method. And we'll call this name. So how do we implement this in our inner assembler? We have to, well, let's review what the inner assembler currently keeps track of. It keeps track of a single section, and then all the symbols that we've encountered so far, and then a list of relocations that we have encountered so far. Well, we're going to have to change this assembler section to be multiple sections because, we want to be able to handle multiple sections. So we're going to have to change this parameter from section to sections, and we'll pass in, or this property will be a list of such sections. And therefore here, we need to create a list of them, not just a single one. And initially that section is empty, or that list of sections is empty. But if we go back to our text assemblers, in all the other cases that we have been writing, we've been assuming that the default or the starting section is one that is executable. It's the text section. So we're going to make the text section the default section when we start assembling. And in order to do so, we're going to create a method called, well, let's see. We can reuse the switch to method that we just defined. So we'll just say, okay, first of all, we need to define a new member variable called current section, which is the current section that we're generating output to, and switch section will return to us that section. So let's go to switch section and change its return to assembler section, and then change this to mode. So we also need another collection which keeps track of all these sections based on their names so that we can quickly look them up. So we'll need to add another member variable called dictionary from a string to an assembler section, and I'll call it sections by name, like this. That looks good. Okay, need to define a member variable called current section, like this. And it's not read-only because this can be changed during the assembly, during the run of the assembler. Okay, so now we just have to create an instance for the sections by name collection. And then we have to go to the switch section function and tell it, all right, check to see if there's such a section already existing. So if it isn't, then we have to, if it doesn't exist, then we have to create one. So we'll do sections by name, try get value, name, out var section, and if it exists, then we'll not enter the if statement, we'll fall out the other end and everything's good. However, if we go into this branch, then we have to create the new section. So we'll say section equals new assembler section, and then we will add it to our dictionary. So, and also to our list of sections. So we'll say sections, add section, and then we'll say sections by name, add name section. But we also need to put the access mode somewhere, and the logical place to do that is to pass it in as a parameter to the assembler section. So let's go ahead and pass in the access mode as a constructor parameter, and then let's go to the constructor here, and then let's add a property of access mode to the assembler section. Voila. So now this I ran into this before. Access mode conflicts with the Risc-V enum with the same name. So we'll need to specifically make sure that we don't access the Risc-V access mode but our own. Good. Well done there. Alrighty then. So we now have to fix the project, because everywhere we're assuming that the assembler only has a single section when in fact it has multiple. Also, to match the way that the ELF file organizes its information, we will want to put relocations. Well, let me think about this. Yeah, I want to be able to associate relocations. So relocations are done on sections. Now I want to associate the relocations for a particular section. So I'm going to move this property relocations into the assembler section as well, because that matches the way that ELF files are laid out. So I will steal this. In fact, I would remove the property relocations and move that into the assembler section as well. So we'll put it right here. And what we'll also want to do is something I noticed that was annoying to me is there's no way to find out how big the assembler section is. You have to call get assembled bytes, which is very expensive because it copies all of the bytes into a new byte array. So I would like to be able to just query the size of this, and the easiest way to do that is to just expose a property called size, which returns the bytes.length cast to an unsigned integer. All right, so that's that. Now we need to fix, now if I build the project, we'll get a lot of errors because we renamed a property without, but we also changed its type. So let's start with this class then. So relocations no longer exist on this object, the assembler. Instead, they are being moved into the current section. So let's change all occurrences of relocations with current section dot relocations. Oh, I'm overdoing it. Then the next error that we get is probably going to be all the places where we talk about the current section. Yes, we're referring it as the previous name, the property called section. Now we're going to just change that to be current section, the member field. So let's see, that one should be replaced, and that one. We'll step through the program replacing these references. All right, so let's be clear what we did here. Previously, before I started refactoring, we had only one section. I replaced the property called sections here with a list of properties. Oh, sorry. This property was a single assembler section. Now it is a list of assembler sections, and all the users of that property have to be updated now. So let's find where they are. And we'll use the compiler to guide us. So here's one place where this is inside a text assembler, and we should just propagate the list of sections out from the internal assemblers sections. Similarly, the relocations, we're no longer exposing that. I'm just going to remove it from here. If you want to get hold of relocations, you should go to the individual sections. So we'll remove that. And then the assembler section, the assembler file method, which previously was returning a single assembler section if everything succeeded. Now it will return a list of assembler sections, or null if there was an error. So that was easy enough. Now let's build this. Now we get more cascading errors here. So when we call the linker, what we want to do now is pass in all the sections. So we'll rename this variable from assemble file, or from section to sections, and then we'll pass that into the linker. So we need to change the linker. And the assembler no longer has relocations, so we're going to remove that from here. And instead what we'll do is we'll go here to the linker, remove this property here, or parameter, and we'll change this from a single section to all the sections that we were able to assemble. And then we'll get rid of this member variable relocations. We don't need it because we can extract all the relocations from every section that we process, so we'll remove that. But then we do want to compute all the PC rels. So what we'll do is we'll use a select many operation to extract all of the relocations from all of the sections. Let's change that to sections. Good. Okay. So now the linker will receive the list of sections. Let's build this file again. Now here we're calling size in bytes, but notice that we can replace that with just, okay, I take that back. We have some problems here, but our refactor will fix this up. So let's just leave this code like this for now. But yes, it is. Well, let's see what's going on here. We're creating the elf builder. Right, what this should be doing is looping through all the sections. And in fact, it will. It has the sections there, so it can do all that work. So, okay, we'll revisit this, but we want to look at other files first before we get there. So go back to the linker. All right, so how does the linker need to change? Well, previously it only had one section to worry about, so its job was pretty simple. It just allocated that single section at a particular address, and then we were done. But now we have to be more more intelligent, because what we need to do is um, we need to measure how big each and every resulting segment is supposed to be on the file. And also we need to lay out all of the chunks of memory in their appropriate places in memory. Currently the layout is here trivial because there's only one section, but now we have to first place all of the sections in their inappropriate places in memory that don't overlap with each other, because we don't want these sections to overlap when they get loaded into memory. So what we'll do is we'll create a new method called place sections or segments, like that. And what we'll do is we'll get the result and store it in segment placements. And then we're going to create a new method called allocate segments. Which will take the sections from the assembler and create segments to store the contents of the sections. And then this memory object goes away. We shouldn't be using memory anymore. We should be using the elf builder. So I'm going to go here and change this to elf builder. And rename this to elf builder. Okay. All right. So we need to declare what is a segment placement. Well, a segment placement is a location, an address, a virtual address, and so we need to keep track of for each assembly segment or section. We need to keep track of where we've decided to place it. So we'll create another dictionary that takes a assembler section and maps it to an unsigned integer, which is its address. And we'll call this segment placements. All right. So let's implement the method place segments. I'll put it here. Private void. Actually, no. Dictionary. And we'll actually need these sections to do this work. So let's pass in the sections. So we're going to create a dictionary of we'll call this the result or placements. Empty dictionary. And then we'll spin through each section. And we also need a starting address, which is something that is provided by the caller. So let's pass that in as well. Actually, it's a member variable, so we can just use the member variable. And we'll say this, or actually the uint uadder equals adder base. And then we spin through each section into sections that were passed in from the assembler. And what we'll do is we'll place this section at the address uadder, like that. But then what we want to do is add the length of the section. This should result in an address that points beyond the end of the section. But we also need to be careful here, because these segments typically want to be aligned on a processor page. So we need to align these up. So we'll need to re-implement that method align up that we had before. We'll just re-implement it here. and it's fairly trivial. We will align them up by a chunk size, which is, oh, I don't know. Let's see. We'll use the memory page size like that. And then that becomes our new address. So the effect of this, what this will have, the effect of this will be that we allocate an address for a particular section in memory, and then we increment it by its own size, but then we also align it up to the next even bytes per page boundary. This way, we always guarantee that every segment that we are going to be creating will be loaded at a page boundary, which is important. So let's implement that then. So align up, we'll take a value and a alignment, and then we just compute the upwards alignment. So that is going to be align, actually it's going to be value plus align minus 1, just like before. We take that number and we divide it by the alignment. This will give us a number, a value that is, it tells us which chunk number the next chunk would be. But then we need to multiply that back up again. So we'll do that. And that is aligning up. Right, so having done that, we now have placements for each segment. So let's return the placements to the color. All right, good. And then what do we do? Relocate. Well, we'll be doing all the relocation in here, I guess. So we can just scratch this and then implement this method. All right, and so how this will work is we will for each var section in sections, we'll want to relocate that section. And what we'll want is to pass in the address of this particular section. So we will say placement of section. Now we have a address. So now we need to implement, oh, we'll do that later. First, we have to relocate the data inside of that section. Once that is done, we can then write it out to our elf file. So we'll say elf builder add segment, and we will give the segment type, which was pt load, and then we need to give it an address, which is going to be, well, let's just extract the address here. We then extract the data from the section and we pass it in here. Then we pass in 0 for the memory size as discussed last time. And the access mode we can now extract from the section itself, which we couldn't before. And then the alignment is going to be the same alignment, which is memory dot bytes per page. And there you have it. We're building the elf file one segment at a time. For each section, we relocate it, and then we create a segment, which is a one-to-one mapping to each section in this particular implementation. That will change in the future, but for now, we're happy with this arrangement. So now we have to implement relocate section. And what relocate section does is It's fairly simple. We just loop through every relocation of this section. So for each relocation or rel in section.relocations, we call relocate, which we already have, but we're going to be passing in the relocation, but also the section in which it lives, and then the address of that section. All right. Then we need to fix our relocate method. Because it needs to be passed in this extra information. So we need the section and the new adder of the section that the relocation is in. Okay, and then we need to clean up and fix some other pieces here. So Elf Builder doesn't allow us to read any data. We still need to be able to read the memory from the section that we're relocating, which is why I needed to add this parameter here. We're going to pass that into here. And then we need to implement a method to read a word at a particular, and the word address here is incorrect, really. It should be offset. It should be the offset in the file where the relocation is. So let's just change that to offset for address here, and then rename this variable offset, because that's really what it is. It's an offset within the section that is being relocated. So then we also need to correct the computation of the displacement, because the symbol that we're referring to might be in a completely different section. So we need the section of the symbol. Right. The symbol needs to know which section it lives in, and it doesn't do that today, I think. It doesn't. So we need to pass in assembler section to the symbol, because we need to be able to ask a symbol which section do you live in. All right, so we'll do that. So now I can ask the symbol, give me your section, and then I'm going to look up where in memory that section will be loaded when it becomes a segment. So we need to get this dot placements of that section. That will give me the address of the section, and then this address field of the symbol is actually the offset within that section. It just so happened that previously the address space was 0 in many of our unit tests, but now we have to refer this address to relative to the section in which it lives, which would be this address. So we'll take that and put it here. But then we also need to compute the, this is a displacement, so we need to make an address out of this as well. So the way to do that is to take the address of the section that the relocation is located in. So what we're doing now is we're computing the actual virtual address of where the symbol locates by taking its, let's rename this to offset just to make it clear. So we're taking the symbol's offset within the section that it lives, and then we add that to the address of the beginning of the section. That will give us the address of the symbol, and then we do a similar thing here where we compute the address of the relocation by taking the offset of the relocation within its section, which is what that is. And then we add to that the address of the section itself. So that will give us a displacement. Then we can use that in our code. And then what we want to do here is replace these with section, because we're not modifying the elf builder. The elf builder does not expose a write LE word 32 method. All right, we got rid of a few errors there. Now we need to go and implement this read word LE word 32. So this is a little endian read to complement the little endian write that we have. So yeah, let's put it in alphabetical order, I suppose, right about here. And we'll change this to public. And then we have to do the same kind of tricks that we're doing for the write method, except now we're reading. So the first thing that we need to do is change this to offset, I suppose. And then we want to place the cursor at that offset. That's what that does. And then we need to read a bunch of bytes. And remember, the little endian order specifies that the first byte that we read is the least valuable, or the lowest in significance. So I'll say byte. Actually, let's just do this. Var uint. The first value, B0, is going to be like that. So we read 1 byte, 2 bytes, 3 bytes, 4 bytes. And then we need to return to these to the caller, but we need to concatenate them together. And starting with the most significant one, which is the last one, because the least significant came first. So we'll take B3, right shift it by 24 to make it most significant, and then B2, right shifted by 16, the next 8 bits, and then B1, right shifted by 8 bits, and then finally B0. That returns the word. All right. We will then continue. Let's build. All right. So now whenever we create a symbol, we have to pass in a section, and it luckily in the internal assembler, the current section is available for that purpose. So that was easy. Next. Right. Oh, this is interesting. So the relocate method, which is called by the client of this class, we'll get an elf builder back. And by the time we reach here, all the work to relocate and load the sections into segments, that has already been done in the constructor of this class. So this function becomes trivial now. It just does nothing. It just returns the elf builder. It's like that. All right, okay. Let's rebuild again. Okay, so we're getting a bunch of warnings. Ah, right. This is great. We no longer need to create an elf builder because the linker will have created it for us. So I'll just trade names here. And then we can discard this line and this line and this line. Everything except that, because we do need to write the entry point address of our executable. But then once that all is done, we can call write to stream. Lovely. Okay. Next file. So this looks like we need to add a method to the inner assembler to add a relocation. I think we already have one. Let me see. No, we don't. Okay, so let's let's go visit the inner assembler, which is over here. And let's see where we find relocations. .add. So we're adding them directly, but we're also creating them. Here we go. We're calling it emit relocation. All right, so let's add another method. It has the same name, but this one takes an already constructed relocation. And then we will just do those 2 lines of code. That was very painless. And then we go back here. So now we can say to the inner assembler. All right. Okie dokie. So now we need to change our unit test because they are going to the assembler and asking it for the number of relocations. But what we want to do here is ask the section for its relocation. So we'll go, and all these unit tests only have one section. So it will be safe to just replace asm.relocations with asm.sections of 0, the only section, and then do that. Okay, let's build this. Here we are again in a scenario where we only have one segment or one section in place, so we'll just grab the 0th section and then let's find some more errors. That's now called offset. And then this is now, again, we want to refer to sections of 0. And then here, the linker no longer accepts relocations because they are all inside the sections now. And then this should be accepting the sections that are coming out of assembler 2. But then this does a relocation, and this is now no longer a memory object, it's an elf builder. So this needs to change as well. Good. And then the test result needs to be changed so that it accepts an elf builder. Okay. Let's try building everything again. We are not initializing the elf builder. That is bad. So we need to create one right before here. So let's just do that. So our elf builder is not a 64-bit. It is not big endian. It will create a executable type. It will return a Risc-V executable. All right. I think most of the errors now are in the unit tests, which need to be adjusted for the new names of all these properties and the fact that we've moved the relocations away. So what we can do here is say var rel equals tasm.sections of 0.relocations. And then we can replace all these with rel. Good. Let's find another place we're using relocations. That needs to go away. And section z. Assert that section z is not null. And then pass in the section s. So this code, what is it doing? Ah, right. We no longer need to do all of this mess because we have that. So we can say and that's it. Okay, good. And then we have to go back to the text assembler because it is not happy about something. All right. Let's just replace all of these references to TASM locations to TASM dot sections of 0 dot relocations. Okay. That drastically shrank the number of errors. So now the linker tests. This DASM needs to take an elf builder. And what do we want to do here? We want to read the bytes. So how do we do this best? Let's find all the colors. This is the only place. Right, so we need to fix this by what we're trying to do is extract the bytes that we wish to disassemble. So we will go to the elf builder and it will have, we'll need to expose the segment data. So segment data like that. And that will become our bytes. So we need to expose the segment data field as a property. So let's go to the elf builder and fix that. So let's make that a public property. And let's move it to where the other properties are. Let's rename that. Good. So now in our linker tests, that is going to be able to extract the segment data that we want. Nice. Okay. And then we need to be able to read from the elf builder. All right, we'll need to create a new method here called read leword 32 like that. And then we need to create that method. And that's going to be taking an array of bytes and then an offset. And then what we'll do is we will do the same dance again. We'll have a byte 0. It's going to be bytes of offset. And then the subsequent bytes again in little endian order. So the little endian is this. This is the least significant value. And then we return B3 shifted right by 24. B2 shifted right by 16. B1 shifted right by 8. And finally B0. So now we are reading a word out of a chunk of bytes instead. And at some future time, maybe all these common pieces of code could get refactored into a utility method. But for now, I'm happy to just put them in here. But it means also that we need to change all the places where we say result.elfbuilder, read le word. We need to change those to read le word 32, and then result.elfbuilder with a capital B maybe, and then segment data, right, of 0, comma. And here we want to capture the left parent. So let's see what happens if we do that. Okay, looks good. That will do that job. All right, let's build again. The number of errors is continually decreasing, and I'm not really adding a lot of functionality here. I'm just exposing or changing the places where properties live. Okay, we fixed that one. That unit test only has one segment. Okay, so here again, we assemble file returns as sections. So we need to assume that those are not null. And then we need to grab a section, which is going to be always the first one in this unit test. So there we grab the first section, and then we can rebuild this. Could it be that we finished our work? No problems detected. How about we run all of our unit tests to see whether there should only be one failing unit test. All the other ones should pass. So hopefully, if we've done everything right, there's a single unit test failing, and that is our friend switch section. Okay, now it's complaining because it's not, well, there's some syntax error. So let's go back and find out what that syntax error might be. So the way to do that is let's go to the assembler. Actually, let's go to the text assembler. We have it right there. And what we want to do is find where we set the error. And then let's run that unit test in the debugger and see why we're getting an error. So in the call stack, we can see that unknown directive, my word. Oh, because it's not a label. Oh, yes. So that's a bug from my end. So let's go back to our text assembler tests, and we forgot the colon for the label. How about that? Now let's try it again. Let's run that test. we still expect it to fail, but this time we should see perfect. So how are we going to get this output visible? If we run this in a unit test, well, let's do this. Let's go to that unit test, run test 2, and let's just print the actual stuff. Let's put a breakpoint right here. Maybe I can copy the output that the assembler is generating. What I'm trying to do is confirm that there are 2 segments in the output here. So let's see what S actual has. Ooh, can I copy this? I cannot. Can I copy it from here? Please let me copy this. Ah, nice. And then I'll put it here. Oh yeah, there we go. Oh, so it's enormous. Now, why is that? That's because we are aligning our sections or segments to 1K boundaries, as you can see. And that's pretty atrocious. So, I need to go back and read up on the ELF spec to see whether this can be done in a manner that makes it a little bit more compact, because obviously this is very wasteful of space in our resulting file. There's too much space being used up here. But here you can see the BBBBBB. But we also see the machine code here. So something didn't go quite as expected here. We're seeing both the, that's a return instruction. There's our data, and then there are those other 2 instructions that I wrote. So there's something wrong in our code. So I will stop here, take a little breath, and then next time we'll try to figure out what went wrong, and maybe also see if we can reduce the size of this file, because right now it is absolutely enormous. And it really could be a lot smaller than this. All right, well, thanks for your attention, and hope you have found this refactoring session interesting. Remember that the source code is always pushed up to the GitHub repository in the description. And yeah, let's come back next time to fix the bug and put a line under our linking adventures, and we'll switch gears again. Until next time, take care, have a good one.